Welcome, everyone. We come from one of Europe's biggest banks, actually. And at Klarna Bank, we provide payment solutions for end customers. They a smooth experience to buy stuff on the internet and also in physical stores nowadays. We have about 60 million users buying stuff from around 90,000 stores in 14 different markets. We're pretty global, and we have almost 2,000 employees. We provide our customers with the ability to pay now, pay later, or slice the payment in a payment plan. And to be able to provide this frictionless experience for the customers, we need to take decisions about ID, fraud, and credit risk. And we need to do that sub-second. Eric's now going to show, or we're going to talk about a small piece of that puzzle at Klarna, and Eric's now going to show the agenda.
Speaking of puzzles, here's the agenda. So first of all, we're going to lay some architectural foundations so that we at least have some technical background on what we have built. And since no architecture is optimal, we're going to talk a bit about the optimization of what we built. And then we're jumping onto the teams, seeing how we organize ourselves, especially since we have a rather small crew taking care of the infrastructure, whereas we have a lot of data producers and a lot of data consumers. That also puts some interesting requirements on the tools that it turned out that we needed to provide. Yeah, that's the outline, I guess. Yeah, so the speakers, I'm Eric, this is Per, and yeah, please contact us later on if you like. You'll find us on LinkedIn. The teams, yeah, we belong to teams. So we actually have two teams that takes care of the data infrastructure, which is basically a Hadoop cluster and some other systems around. More about that in a bit. As you can see, the teams are rather small for a company with 60 million customers with presence on 14 plus markets. So it's interesting to ask yourself a question, how did we make it? Well, so what is it that we run? More specifically, it's a Hadoop distribution from this company called Hortonworks. And we do have data sources that we ingest into this system. I think we have about 100 or 200 data sources, something like that, right?
Yeah, 200. Yeah.
Yeah, let's say 200 plus and counting, because that's closer to the truth, I guess. Data sources include, as you can see, message queues, Kafka topics, relational databases, and cloud sources of various kinds, including web sources. All these data sources, they are landing in the distributed file system on the left-hand side here on the picture. And then our data consumers are running the transformations here to feed business insights, to improve user experience, to do these critical services for ID risk and fraud, as we mentioned. The results of the transformations are materialized on the right-hand side of the distributed file system. And what's interesting about these transformations is that they are owned not by us, but by the data consumers themselves. And that puts interesting requirements on how should these transformations be maintained and deployed and so on. More about that in a bit. These transformations land on the right-hand side of the distributed file system, and some of these are exported then to these mission-critical services that Pelle mentioned at the beginning. As you can imagine, it is rather critical that the results of these transformations are modeled in the proper way so that we can respond in sub-second or sub-100 milliseconds to each of these other services to provide a smooth buying experience for all our customers while minimizing fraud and risk. Oh, and we have analysts. So this analyst in the bottom right corner of the picture, she is interacting with data, both on the input and output side, obviously. And look what she's doing. She's looking at the yellow arrow on her screen, and she's trying actually to compare that yellow arrow to an updated variant of that, which is colored in blue here. Oh, am I in the way? Which is colored in blue. So she's trying to determine which one is the smartest. More about that in a bit. Some fun facts. We have a respectable amount of storage. We never had data loss. This is fantastic for any kind of infrastructure. We never had data loss. We never had any unplanned downtime. We had planned downtime, I can assure you that, but no unplanned downtime. That's fantastic. We have, some 100 human users and machine users. We have 9,000 Hive databases.
Why, Eric? Why do we have 9,000 databases and like burn 30,000 CPU hours a day? Why is that, Eric?
That's because Lambda.
Yeah, Lambda.
Lambda. Anybody heard about Lambda architecture? Anybody using Lambda architecture? Anybody think Lambda architecture is obsoleted? Yeah.
Nice.
That's the usual kind of response you get. And that's okay. Why are we using Lambda architecture? We are supposed to be modern, right? So a quick recap of what is Lambda. Well, on the left-hand side, we have the source of truth, which is an immutable stream of events, basically. We have the transformation, now it's colored in gray for some reason, and we have the transformation result. The important thing about Lambda architecture is that each event that is landing on this side is immutable. You can never change anything that has happened. Instead, it's an insert only, if you like. Whatever function you apply is written in such a fashion that it is a function of all data. So whenever you apply this function, you run it on all the terabytes of input data you have. Boom. It takes some time, but it's robust. And it is this robustness property that we really like about Lambda architecture. Another nice thing about Lambda is the expressiveness of it. So the combination of immutability and recomputation makes it easy to express, easier at least, by any standard, to express any transformation you want to express on, you want to apply on the data. I actually remember, do we have time for an anecdote?
You do, Eric, you do.
Thank you. So I remember actually 25 years ago, I was in high school and I was taking a class in German, and I was at this final exam, and I was supposed to write a short essay about Goethe, Bach, and Luther, I think. And I started wondering how much should I be writing here. So I actually called on the teacher and asked, okay, how many words should I write here? And she was looking at me, and then she told me, Eric, write as little as possible, because then you'll make as few mistakes as possible. And first I thought she was sarcastic, right? But then I realized that this is actually a piece of wisdom that she's sharing with me. If you write as little as possible, if you can increase, translated in terms of computer science, if you can increase the level of abstraction so that you can express your ideas as briefly as possible, then chances are you will make less mistakes. That's the wisdom. Okay, and another super powerful feature of the Lambda architecture is that if you introduce versioned transformations and combine that with the Lambda architecture, you can maintain several versions of a transformation simultaneously. They will run in parallel on the same input data, so then you can compare the results as well. So this comparability plus Lambda gives us continuous improvement, which is a rather powerful feature as well. As we have stated already, Lambda comes at a cost, and that's CPU cost. So now please, software engineer, tell us about optimizations.
Yeah, so of course 5 years down the road we have made some optimizations, and we have of course also looked on the Kappa architecture. So in truth we run like we provide the Lambda architecture, but pieces of it is actually more like Kappa. So down the years we noticed that we can categorize our transformations in 3 different types of transformations. Being linear prediction, single source aggregation, and finally general data processing. The thing with linear predictions are they are basically pure functions. One row, you apply a function, you get an output. The same data always gives the same output. Rows doesn't affect each other. Single source aggregation, that's like windowing on let's say 3-day basis, 72 hours, something like that. Good for velocity counts, aggregate sessions, stuff like that. And then you have the general data processing. That's the Lambda, that's function of all data basically. You join whatever you want with something else. So we notice then that linear projections, they are easy to make incremental, history doesn't change, events are immutable, function is pure. That means that's an append-only thing. Single source aggregates, they also, they not append only, but they have a huge historic tail and a small 72-hour or weekly or monthly head. So those are also easy to make incremental, and you can save a lot of time and CPU hours by not recomputing everything. Once you get into this area, you still need to do functional wall data, and that means increments are hard. We also noticed that most of our important domain logic is, of course, on the right-hand side. Linear projections, that's mostly normalizing, picking some feeds, stuff like that. And single source aggregation, that's also low-level aggregates that doesn't change that often. Did I press a button?
Perhaps
It doesn't matter.
Sorry.
Yeah, it doesn't matter. So, segue into code changes. We also noticed that code changes more on this side than on that side, which means there will be more recomputes on this side and less recomputes on that side. With that said, since this is more like Kappa doing the incremental processing, we can still do recomputes from like 10 years back, both on all these arrows, basically. Another issue we have been having with big data, and I think all do, is that it's hard to cross system boundaries with big data sets. And the Lambda architecture produces batches every day for us, and that means we would ship a huge batch every day to some sort of serving layer. That really doesn't work. So, well, it doesn't work for big data sets anyway. So we came up with a way to sort of make an incremental data export. Although we have new batches every day, we figured out that if we take yesterday's batch and today's batch, we calculate the diff, we can synthesize a transaction log and ship that one, much like bottled water or Golden Gate. So basically, it's a change data capture synthesized, and on the consumer end, you just do your inserts and updates. So that works for us, and you can cut down a lot on what data ship every day. Right.
So now that we have sufficient technical meat, we can take a step back again and look at this architectural slide. And look what I did. I enriched it with data producers on this side, because these are the data sources. Data consumers on this side, because, well, we got the data consumers here and the target tables and what have you. And the infra in the middle. And as I indicated already, we have hundreds of data sources. We have actually hundreds of software engineers who are producing data for us. On this side, we have the usual zoo of data consumers, including data pipeline engineers, we have risk engineers, fraud engineers, we have analysts of different kinds, ranging from anything from business analysts to data scientists. So they are also in the hundreds. And as we said, we are a skeleton crew. So that puts some question on how do we organize ourselves? Where do we put the boundaries of responsibility? And I'm sure you can have some opinion on that.
Sure. So early on, 5 years ago, we figured that to be able to scale our organization, we need to have these three entities: producer, consumer, and infra. And we need to have relationships between them. But we need to stick the domain to the producers and the consumers. The infra cannot be bogged down by domain choices, domain knowledge, stuff like that, because we need to care about providing good infrastructure to producers and consumers so they can solve their important use cases. They are the experts on that. We are the experts on providing infrastructure. So this also means that the consumer needs will drive the producer quality. So a consumer will say, hey, I can't use this weird timestamp format. Can you please fix that so I can solve my very important use case? So the full domain knowledge is here, and that communication should happen there. However, there's a lot of friction trying to get a producer to understand he's really a data producer, because he usually has a totally different use case, and he just sees a couple of logs down there. He doesn't really care about them. So you need to facilitate this and tell the consumers, go to the producers, tell them you're using this data, tell them about your important use case, and make them deliver better data to you guys. So a few small simple scenarios just to understand the model. A consumer looks at the data set, says, hey, what does this field mean? Of course, he goes to the producer and asks that. We have no central thing where you go and ask that. On the other hand, when a job crashes and the consumer can't find the reason on his own, he will talk to infra. Hopefully, we have good tooling in place so he can find all the logs and the reason on his own. What we also did, we set up a Slack channel for all consumers and producers where they can ask questions. It's our support channel, basically. What happened was that consumers started answering other consumers' questions in the Slack channel. And nowadays, I think that we probably answer about consumers answer about 60% of the questions before infra has time to answer. And it will be highly technical questions as well. So we basically have a couple of senior consumers that basically take honor in answering these questions. So building this internal community really helps taking pressure off infra. Right, another scenario. Consumer says, hey, we want your data to producer. A producer says to us, hey, can you ingest the data because the consumer needs it? And we do that, and then we say, hey, consumer, here's processing power. Start doing your use case. But we don't want that kind of communication all the time. This is bread and butter of an infrastructure. So we provide tooling for this, of course. So we provide standardized data ingestion that we hand over to the producer, and we provide some sort of transformation packaging that we hand over to the consumers so they can service themselves, basically.
Yeah, so speaking about self-service, and so what is this high-level transformation packaging, and why do we call it that? Yeah, or HLTP, if you like. So basically, it's a combination of integrated technologies. Remember those yellow arrows that later were gray and later were blue? If we think of those as a transformation, that's a T in the HLTP, right? So the high-level packaging of transformations, that's the way you could think about it. Each transformation is normally one or more high queries. We have several transformations that consist of hundreds of high queries, actually, which do take a few hours to execute from start to end. So what the analysts or engineers that maintain the transformations are doing using HLTP is that they version the transformation using Git. They deploy the transformations using, release and deploy them using Jenkins. They have this artifact repo in Nexus. And we also generate Uzi scheduling. It was observed early on that Uzi was very reliable and very scalable. So it did a job that you can expect from a job scheduler. On the other hand, the usability was not that great. So what we did in HLTP was also to provide a DSL for our analysts and users, for our data consumers, so that they can express on a very high level scheduling specifications and data dependencies and things like that. Remember what I said about the German teacher before. Try to raise the abstraction level as high as possible, because then you'll make less mistakes. This is what we did in HLTP as well. So with HLTP, we have empowered the data consumers to maintain the whole life cycle of data transformations themselves without any hand-holding from the data infra team. And that's super powerful by any standard. So what happens once such a transformation, HLTP transformation, completes? Well, a Hive database is generated, which is called something. In this case, it's my job version 1. Remember, it's version, right? and then it's time-stamped, in this case with a day. This is yesterday, or 18th of April, right? So this is a Hive database with 2 tables. And that's the result of a transformation. And as soon as this database is materialized, the data consumer can start query it, or any downstream dependencies can start use it. Remember that one man's data consumer is another man's data producer. So we can actually chain data transformations, having them depend on each other, which is rather cool as well, all packaged using HLTP. The next day we'll generate another database with a new timestamp. That's today's database. And tomorrow there will be another one. And for each transformation, there will be such a sequence of Hive databases. Here's another Hive database. It's their job, version 2, they have been working on.
So 9,000 databases starts to make sense now.
Yes, sir, 9,000 databases. But Hive databases are cheap, whereas troubleshooting time is expensive. So we rather have many Hive databases around. To put a limit on the Hive databases, however, we also have a feature in this HLTP, high-level transformation packaging, that allows the analyst to specify how many of these Hive databases do I want to maintain. Is it 1, only the latest one? Is it 3, 5, 7? Any number. Normally, analysts go for 3 databases because 3 is good. Okay, so another problem that arises is how do I search for these Hive databases, given that they come in the thousands? Yeah, so that's another tool that we build that we call named dataset discovery, which basically enables the users to find the latest and greatest Hive database of each kind of transformation. They can even discover the latest and greatest given a certain major, minor, or fixed version, which is also rather powerful. And yeah, this gets so exciting. So high-level transformation packaging, dataset discovery, and we have a third one that is actually open sourced by us, which is called Hive Runner, which is an open source unit testing framework for Hive. It runs on your local computer. You can integrate it with your IDE, and doing so, you can unit test your Hive queries. You can even unit test or integration test your entire workflow of hundreds of Hive queries on your local computer, which again is a rather super powerful thing. Why do you want to work on local computer? Because there is no such thing as 127.0.0.1. So this tool suite combined enables the data consumers to manage the entire data transformation lifecycle, including test, release, deploy, schedule, and troubleshooting. So this is what we had to build, given that we have hundreds of data producers, data consumers, and are very lean on infra. Okay, but things aren't always as rosy. Suddenly comes a data consumer that says, our mission-critical data transformation suddenly takes 3 times longer. And going from 4 hours to 12 hours is usually not okay. So they need help. And there comes another data producer, actually, who doesn't know how to query this JSON data. Perhaps it's broken, perhaps it's some other problem, and they need help from us. And there is another mission-critical data transformation that keeps crashing, so it's rather urgent. So what we had to do is to introduce something that we call professional services, and that's people made of flesh and blood. Per, I think you have a remark or two on this. No, you don't. No, this is for me. Yeah, so this domain that we before said should be some kind of agreement between producer and consumer. Well, yeah, that's sort of modulo this professional services. So right now it's a couple of data engineers who have seen a lot of Hive queries in their days, who make up this professional services team, and they usually are able to help out with these kinds of queries, with these kinds of problems. And one question we started to ask ourselves then is also, if we are tasked with helping our users be more efficient and avoid trouble when running these high queries, is there any chance for us to be proactive? Yes, let's build some kind of dashboarding showing the most heavy hitters and being able and enable us to spot trends. What kind of queries, what kind of transformations have started to take most time? Are we able to help them applying some cheap tricks, or do we need to apply some science even to be able to help them? So we started an elk stack that is feeding purely on performance data from the Hadoop cluster. And using this, we can make discoveries such as 40 analysts are actually querying this in this data source in a rather suboptimal way. And now we can help them be smarter. So this is cheesy, but we call it proactive professional services. Okay. And one more thing, actually. So given that we have this proactivity in professional services, and we actually can help the transformations owners from time to time with these kinds of results, we get the question back, okay, this is fast and this is good, but is it correct? Otherwise, these improvements are not worth so much, actually. So enter another tool that we made called diphthong. It's in Swedish, sorry about that. But what it gives us is the ability to, on large scale, compare Hive databases, table by table, row by row, cell by cell, and then be able to spot the needles in the haystack. And that, if we run that on the two different versions, the one that took, let's say, 1,000 CPU hours, compare that to the one that took 3 CPU hours, and if we can prove that they're equivalent, there are no differences here in these terabytes of data, then we're good. Then we have done a good day at work. Okay. Yeah, let's stop with the planet slide. Pelle, why are the planets here?
Did you put them there, Eric?
I think these planets are yours.
Yeah, mine. Okay, so basically we call it the Hadoop ecosystem, right? And these are two ecosystems. One is blue, green, and lush. You would like to be there. And this is the chaos planet, basically. And if you work with Hadoop for a while, you know that at times it feels like you're on the chaos planet. But what we really try to do with this pick model is that we try to keep producers and consumers on the lush planet, and we take the problems of the chaos planet, basically. So try to keep your producers on the nice green and blue planet and live there because you know how to survive there, basically. Your users, they can't survive there. That's the final words. So,
yay.
Questions?
Yes.
Yes. So not Lambda functions, but Lambda architecture.
Right,
yes.
So in order to compensate for some of the services, this is actually interesting. For some of the services, it is not really okay to have this turnaround time of a batch, right? So in those cases, we need to compensate for that using the speed layer. And the speed layer is implemented outside of the Hadoop cluster.
Yeah, we noticed early on that speed is needed, but also expensive. So that's case-by-case implementation of speed layers. Sure.
I think so, yeah, I think we have time.
Very short. No, it's not. Not yet, anyway. But I think we have a. I think we have a master thesis on that one.
Yeah.
So it's. I guess it's good chance it will be public.
Yeah. It will most likely be public.
Yeah. Yes. Well, sorry, this is going to be a boring answer, but since I'm in the eye of the pick model, I really don't know. Because we tell consumers to talk to producers. But there's actually a couple of consumers down here on the first row, so you can ask them afterwards.
It's the two of us.
When
No, this is enterprise-wide. All our data is there. So
yeah.
Any domains you can think of, they are there.
No, I mean when we say domain, we mean as in our company's domain. So it's the full company data knowledge. That's the domain basically. So we only have one domain. Yeah. So the real-time layers, they don't access Hadoop data. So in the Lambda architecture, the real-time layers, it lives in parallel to the batch layer basically, and is joined out on the serving layer. So if you remember the picture, trying to go back here a while. Oh, Eric will click me there instead.
Yeah, I will take you there. Oy, oy, oy. Yeah, let's reason about the architecture. This is a good one.
Yeah. So basically, the speed layer would be a totally different architecture, probably feeding from these Kafka streams, doing some Spark or something, some streamish, and then ending up in the same serving layer. So when the application makes a query, it would query over either an already merged data set, or it would query two data sets, being one batch data set and one speed layer data set. Was that answer enough? No, cool. Yeah.
Do you take care of the Kafka cluster as well in terms of the certain producers who connect to the Kafka cluster?
Yes, we run the Kafka clusters.
And from the edge, let's say that way, how do you connect to that?
Our responsibility starts with the Kafka. So it's up to the data producer to land the data on Kafka.
So do you provide them with any knowledge? I mean, with NiFi knowledge or something like that? Or is it just really send us the data?
So I'm not really sure where we're talking about, but this arrow between the stream and the data vault, or
Before that, yeah. So our data infra is running the Kafka clusters, right?
yeah.
And what we provide them is basically, these are the Kafka cluster addresses and so on. This is how you authenticate, and that's it.
Yeah, they get nothing special other than all the libraries out there for Kafka.
They also get their address to the schema registry and what have you.
So we have we don't enforce it, but we try to persuade them to use Avro, actually Confluent Avro. So that gives us some schemas at least. Yeah.
Yes.
That's another talk, I guess, but we do handle it, and I think pretty well actually. But we as all companies work really hard on GDPR, but I think we're on top of it. It feels like that anyway. So going pretty well, but it puts stress on some architectures and some scales with it. So I can't really say more than that, I guess. Yeah. Sorry?
From Kafka, you mean?
Yeah.
Yeah, they're hitting Hive.
Yeah, like 99% uses Hive, and that's what we support. Sorry, that's what's supported. We have some users doing other stuff, but that's unsupported from us. Hive? Yes and no. It's fast enough for Lambda batch computations, I think it's a bit uninteractive for ad hoc queries. So yes and no. Yeah.
So if they are running anything on their own, they are basically on their own, and we prefer not to have it that way.
Yeah, I mean, they can run other stuff, but when it comes to Flink or Spark on the same cluster, then the usual answer is no, because we will have issues with resources and SLAs at the end of it.
So for some use cases, we have seen that some of the data consumers is actually preparing a batch in the Hadoop cluster on-prem, and then they export whatever result they have to a Spark cluster in the cloud, and there they are doing heavyweight data science experiments that would otherwise have interfered with the production transformations. Yep.
Curious about your answer regarding hybrid, possibly less than interactive. Are you already using LLAP as well? Not yet. Okay.
we also had some issues with.
I think we had some issues with turning on LLAP, so we are looking forward to HTTP3.
Yeah, we're running a Kerberized cluster, and I don't think LLAP supports that at the moment, so that's an issue, right?
Probably retry with some latest versions. That should be sorted.
Okay, cool.
Eric said he wasn't very fond of the Lambda architecture. What's the preference?
Oh, did I say that?
Well, you raised your hand when
Oh, that was just setting an example. Yeah. Sorry.
It has played us well. It is old and it's bashed upon, but depends on how your data sources looks, what kind of legacy you have in other data systems, stuff like that. Lambda really works out for us.
You know, it's actually an interesting question. Would it be more modern to be pure Kappa, for instance, or be pure streaming? But one of the limiting factors when going pure streaming and throwing out Hive and say we're not going to do any SQL anymore, then you'll have to explain to these hundreds of data consumers why can't they use SQL anymore. Half of them, if not more, are more or less married to SQL. So it's going to be difficult to say just say no to Hive.
I also say, in regards of the Kappa architecture, I think now we start to see real solutions coming for Kappa, but they haven't been around for even a year, basically. It's one thing to run Kappa on 3 months of data. It's another thing to run Kappa on 7 years of data. That's difference. But I mean, we start to seeing better. What was that system? We missed the talk, but like a stream storage. That's something you really need to be able to run a resilient Kappa architecture, and those are soon to be here. Right, and you have been very good to us this late today. Yeah. Both. Yeah. Depends on the ingestion, I would say.
Any more questions will be available offline as well.
Yeah. Thanks a bunch, guys.
Thank you.